Alright everybody, why don't we go ahead and expand this particular function, which is discontinuous at 0, you can see from here, in a Fourier series. Okay. The good thing is I'll scroll slightly up because I have everything that I need right up here. So basically the goal is to just representing this way, which we already have. I need to get a0, I need to get an, I need to get bn. So once we have these, the process is more like integration and some trigonometric identities, and doing our best to come up with this Fourier series coefficients. Okay, but I want to understand what this function looks like at first. Okay, here is what it says: less than 0, and okay, actually let's write it. This is x, this is f of x. Okay, and this goes from like let's say pi to minus pi. Okay, and here's what it kind of looks like when I'm lower than 0. When my x is equal to 0, what I get is pi, right? Pi minus 0. So let's call right over here. This is pi. And it linearly decreases because there's a minus x to it. And it reaches when I have x is equal to pi, it becomes 0, right? Pi minus pi. So I have now this then. And the question is, I always need to have this expansion in which particular interval, and it goes from minus p to p, right? So my question is, what is p? Well, it's right here, right? It goes from minus pi to pi. So from here, it will be minus pi to pi. So I know my p value then in my equations, okay? So let's go ahead and write the a0. I remember that was on the easier side. 1 by p, integral from minus p to p, f of x dx. Remembering that this was 1 over pi right up there, right? When I have from minus pi to 0, what will happen is this will vanish, right? Minus pi to 0, what I will get is I will get 0 dx, plus when I have from 0 to pi, I will have myself pi minus x dx. Okay, then let's go ahead and take this integral, which doesn't seem too bad, right? 1 over pi, the integral will be pi x minus x squared by 2, and I need to evaluate this in the range from pi to 0. Okay, so let's write a0 will be equal to then 1 by pi times, okay, so when I put 0, both will be vanishing, so I'm just going to deal with the pi term, so that's going to be pi squared, right, minus, pi squared by 2, okay, so this will be 1 by pi times pi squared by 2, so I get myself pi by 2, okay, so now I know my a0, it's going to be pi by 2. The next expansion, if I go back to the previous segment, you can see now I find my a0 value, but remember it's a0 by 2, right, when you put it there. So a0 I already get. So now I'm going to have this infinite term. I have to first deal with the cosine one, which is the an term, and you can see it's represented with respect to cosine. So let's see what happens, okay. Typically what happens, just to give you additional information, is when I have like, if this was having some kind of a sine or cosine, then you have to deal with trigonometric identities. Whenever I have x, typically I have to do some type of a integration by parts. Okay, let's proceed. Let's change the color because we're starting fresh. 1 by p minus p to p f of x times cosine of n pi x by p dx. Okay, so this is going to be 1 by pi. As I demonstrated in here, I'm not going to write this way anymore. Okay, so this will be 0 because the function is 0. So I'm just going to deal with 0 to pi. Okay, so I go from 0 to pi. It's going to be pi minus x cosine. Now let's look at this n pi x. So pi is p. So you can see from here these two are the same. So I'm going to get cosine n x, right? dx. Okay, fine. So now let's do them. 1 by pi. Then I'll have pi cosine n pi dx, which pi's will cancel in this particular case. And then I will get myself minus, let's not forget the minus, 1 by pi, this time, x cosine nx dx. Okay. So the first one is fairly easy. So let's start with the first one. So we will have, well, integral of cosine nx will be 1 over n sine nx, right? And I need to put this from 0 to pi. Okay. What about the second one? The second one, let's look at it. 1 over pi, an integral of x cosine nx dx. So I couldn't able to do anything about this just yet. So basically, as I mentioned, we have to do integration by parts. U will be x, so du will be dx. I've done the integration by parts in many modules when I was covering the ODEs, so you may want to refresh your mind from that. dv is equal to cosine nx dx. So then I will have my v to be 1 over n sine nx. Let me see whether I made a mistake. No, this looks good. Very good. Okay. So then I will go back and write this way. So I'm just actually at this point dealing with this. Okay. I want to just evaluate this. Let's put the red font so we are consistent. So this will be uv, right? X by n sine nx minus v du. So v du will be integral of 1 by n sine nx dx. So if I just do this, I will get myself x by n sine nx, which stays exactly where it's at. Well, when I take the integral of sine, I'm going to get cosine, but negative cosine, right? So it'll be 1 by another n, so it's going to be n squared cosine of nx. This needs to be from, well, 0 to pi, right? I also forget that here, right? 0 to pi. I forgot up here too. 0 to pi, 0 to pi. I'm sorry about that. Okay, so this is what I have. So when I, let's go back to the purple font where I could be combining things. So the first thing is to have this minus 1 over pi times this. Okay, that's what I'm going to analyze now. Also, I have to have this, right? 1 by n sine nx minus x by n pi, right? Let's not forget the pi, sine nx minus, because there's a minus in front of it, right? Don't forget that. 1 by n squared pi cosine of nx. And I have to evaluate this whole, all of them, from 0 to pi. Okay. So I have done this a few times, so I'm not going to do this over and over again. But when I put pi over here and 0 over there, I will get 0. Okay, both of them. Sine and pi is 0. Sine 0 is 0, right? Well, it's the same thing over here. So you can see the only difference is there's an x, right? But that doesn't change anything because sine nx is 0 regardless. So the only thing that I'm left with is the last term over there. Minus, don't not forget the minus. So it's going to be cosine and pi. Minus becomes plus cosine of 0, right? Divided by n squared pi. Interesting. So right off the bat, I know this was 1. How about cosine and pi? Okay, I discussed this cosine and pi when I first started the conversation about the Fourier series, but cosine n pi will be equal to, well, when n is equal to 1, this will be minus 1 because this is cosine of 180. When n is equal to 2, this will get me, 360, which is 0, so that will be plus 1. So in order to express this, we are going to use n. And you can keep going if you choose to, but I keep going back and forth to the same point. So this is 0 slash 360 or 2 pi. This is pi, right? So I keep circling this at the end of the day. If I have 3 pi, for instance, that will be right this point again. If I have 4 pi, it's here, right? Minus 1 to the power of n is kind of important, okay? So note this, please. And from here, you can see that my an, when all said and done, it will be 1 minus 1 to the power of n by n squared pi. Nice. I get myself an too. So I'm done with a component, right? So the process was I first find a0. Well, order is not important, but from the easy to hard. a0, it will be first found, and that was pi by 2. And then I went ahead and find an. So you can see from here that I'm done with these two parameters that I need. Fourier series coefficients. The only thing left is Bn. I have a feeling that the Bn will be very similar, except when I take the integral, it will be different, cosine versus sine, right? So Bn, I'm just copy pasting from there. 1 by p minus p to p f of x sine n pi x by p dx. Okay. So if I go and plug it in, just like I did in the previous an value, this is going to be 1 by pi. Minus pi to 0 section will be 0, so I only have to deal with 0 to pi, and this will be pi minus x times sine of, well, as I mentioned before, pi is going to be pi, p pi gone, right? Sine nx dx. Okay, So very similar to the previous approach. So I'm going to separate them. 1 by pi, 0 to pi, pi sine nx dx minus, now I will have 1 by pi again, then integral from 0 to pi x sine nx dx. Okay. All right. So the first term is fairly manageable, so pi's will cancel. I will get 1 by n cosine nx, but never ever forget the negative in front of it, right? So let's not forget this. And I have to evaluate this from 0 to pi. So the second one will be from minus 1 by pi. Let's I'll come back and write it in here, but in another form. Let's do this. U is equal to x, du is equal to dx, dv is equal to, this time around, sine of nx, and my v will be negative 1 by n cosine of nx, right? So now I'm going to write here, I'm going to go back to that line, and let's write this in. I will get myself uv, so x by n cosine nx. Now I will have plus 1 by n cosine of nx dx, right? And I need to do from 0 to pi over here. This needs to be evaluated from 0 to pi here, and this is close the parentheses. So then let me go back over here. Now what I will get is that my bn will be minus 1 by n cosine of nx, okay, plus, let's look at it, because plus, negative comes plus, x by pi n cosine of nx minus 1 by pi n. Okay, the integral of that will be 1 over n, right? So n squared, and this will be sine nx. Okay, and this whole thing needs to be evaluated from 0 to pi. So, okay, let's evaluate it. Like bn will be equal to minus 1 by n cosine of n pi minus 1 to the power of n. I just did it in this very question. Minus 1, right? Cosine 0. So far, this is the very first term. Let's look at the second term. X is pi, so it's going to be pi by pi n, the first term. Cosine n pi will be minus 1 to the power of n. When I put x is equal to 0, you can see that this is multiplied by 0. Although cosine 0 is 1, that vanishes. Okay. How about sine? I did this multiple times. When I put pi, it will be 0. When I put 0, it will be 0. So that last term is gone. Okay. So you can see here there's some calculation, cancellation. So the pi's cancel, but there's something interesting happening over here. Do you see that? This term and this term. Look at it. Both are multiplied by, they are being summed, but one is multiplied by 1 over n, the other one is minus 1 over n, and you sum them up. This is gone, this is gone. So when all said and done, minus minus, well, I got fairly nice bn over here. 1 by n. Nice. I'm happy now. Okay. So now, when all said and done, you have to go back and rewrite this fx as it was pi over 2, a0. So I'm going to write a0 by 2, which is pi over 4, plus from n is equal to 1 to infinity. Well, an was, let me write it, then I'll go back and check. 1 minus minus 1 to the power of n divided by n squared pi, I think, cosine of nx, right? That's what we had. Well, let me finish it, then I'll go back. Bn is, that's for sure, 1 over n sine of nx. And let's do this nx is this way as well, so there's no confusion. So one thing that is leaving is what is an is 1. Yeah, I was lucky. Okay, so this is fairly good now. So I can box this up, and then I can say finally that I have a Fourier series expansion of that particular function. Okay, thank you for watching this video. That's all I have. I will come back with Fourier sine and cosine series. Okay, thanks.